So the wave equation is an important partial differential equation, but arguably more important and more useful is the heat equation. So the heat equation can be used to model how heat moves through an object, but also anything else that relies on diffusion. So for instance, if you dump some pollutant into a lake and you want to see how the concentration gradient behaves as the pollutant spreads out, or if you want to model the spread of a disease in a population, or if you want to model how a meme or idea moves through a social network, you can use the heat equation to model any of these. So it's really, really useful. So we're going to look just in one dimension. So we'll let U xt be the temperature of a metal rod at location X at time t. So just like we saw for the wave equation, if we take like a bar, say of length L, so here's the interval from 0 to L, this is the x-axis, and we start off with, say we drop like a hot coal right onto some portion of the bar right here, then the temperature profile might look something like this at right when we start, so at time 0. So here's the heat profile at time 0. And then as the heat begins to spread, the portions out here and here are going to warm up, and this part in the middle is going to cool down. And so like a minute later or something like that, we might have a heat profile that looks something like this. So maybe this is UX1. And I guess I'm thinking that we're cooling the ends here. We're allowing heat to leave the bar at the right and left side. So maybe we've got the bar submerged in an ice water bath or something at the ends. And as time continues to decrease, we'll get something that looks like this, and then gradually it will just flatten out and vanish. So that's an example of how the heat equation might evolve a particular initial heat profile or initial condition. It can be derived. Oh, sorry, I didn't give it to you yet. Okay, so the heat equation, what is it? It's the first time derivative is proportional to the second space derivative. And so here, A is the thermal diffusivity. So that's a measure of conductiveness, like how quickly heat can propagate through the material. So something like metal would have a large A value. Something like foam or I don't know, maybe ceramic might have an A value that's positive but very close to 0. And just like for the wave equation, we can make the observation that instead of acceleration, we have velocity is proportional to curvature. All right. And so we're not going to worry about where this equation comes from. It can be derived using conservation of heat equations. Most PDEs come from some conservation of energy equation, some kind of conservation equation. We're just going to look at how to verify a solution. So we're going to verify that the function e to the minus a k squared t sine kx is a solution. And so again, the way that we check to see if a given formula is a solution is we're going to take it and we're going to substitute it into the left side. So in other words, differentiate it by t, see what we get. And then we're also going to substitute it into the right side. So take its second x derivative and then multiply by a, and see if we get the same thing both ways. And again, don't worry about where this solution comes from. I'm not going to ask you to construct solutions to differential equations. If you want to do that, you can take Math 418, and maybe I'll see you again there because I love teaching that class. Okay, so let's see. So we'll do the time derivative first. So this is ddt of the business here. And so when we differentiate with respect to t, we notice that there are no t's in this sine portion here, so that's just a constant as far as we're concerned. And we just differentiate the exponential, and it kicks out a copy of its exponent. And then we get the same thing left behind. And then we have that constant sine kx. Okay, and so now let's do du dx, first space derivative. And so for the space derivative, we've got no x's in this first part, so that's just a constant. So we'll get an e to the minus a k squared t out front. Then sine is going to become cosine. And then the chain rule is going to kick out a copy of the coefficient inside the argument of the sine there, so we get a k. Okay, and now we look at the second derivative with respect to x. So I'm differentiating the thing we did in the previous step. And so let's see. So once again, that whole first part just comes through. Oops. The square is on the k. And we differentiate the cosine, and we get a minus sine kx, and it kicks out a copy of k. So now we have a k squared there. And so now that's the second derivative of u with respect to x. So if we multiply it by a to get a times the second derivative of u with respect to x, then we would have minus a k squared e to the minus a k squared t sine x, which you can see, sure enough, matches with what we had before. So we verified that this equation, the given formula is a solution of this partial differential equation.